Okay, so let's get started here. So first of all, I'd really like to thank the organizers, especially for pulling off this conference. As an online conference under the situation. It's been great so far. So let me go ahead and get started here. So, okay, so I'll start with the first half of this talk will be about examples. So I'm going to talk about gravitational instantons, and so I'll just start with the definition. So I'm on a real four-dimensional manifold with a Riemannian metric G. So I'll call it a gravitational instanton if the metric is complete, if the holonomy is contained in SU2, and the L2 norm of the curvature is finite. Okay. So let me explain why, a couple of slides, why we're interested in these things and why they're called gravitational instantons. So, well, the condition that the holonomy of a metric in dimension 4 is in SU2, this is a condition called Calabi-Yau. So this is if and only if the metric is a Kähler metric, so X is a Kähler manifold, and the canonical bundle K sub X is trivial. Okay, so now there's another condition that holonomy is contained in SP1. So this is a condition that's called hyperkähler. So that's if and only if there exists three complex structures, I, J, and K, which satisfy the quaternion relations, such that G is Kähler with respect to an S2's worth of complex structures. So take a linear combination, such as the coefficients are in S2. So this is called hyperkähler. So, well, we're in real dimension 4, and SP1 happens to be equal to SU2, so these notions are equivalent. Okay. So why do we call it a gravitational instanton? Let me explain this a little bit. So the Calabi-Yau condition implies that there exists a parallel 2-0 form, which we call capital omega, and that's written as omega sub j plus I omega k, and those are actually the Kähler forms for these other two complex structures. So my base complex structure is I here, and that Kähler form is omega without the subscript. So then the real bundle, lambda 2 plus, so this is the bundle of self-dual two forms. So this decomposes as multiples of the Kähler form plus the real part of the 2-0 form. So it's lambda 2-0, direct sum lambda 0 to the real part of that. And so, well, the Kähler form omega is parallel. And so this capital omega is parallel. So this bundle has a basis of parallel sections. So that implies that the bundle is flat. So it's well known that the curvature of this bundle, lambda 2 plus, is, well, it has to be 0. We just showed it's flat. So, but it can be written in terms of the Riemannian curvature components. So it's two 3x3 matrix blocks. So the self-dual block is omega plus, is W plus, the self-dual part of the Weyl curvature, plus the scalar curvature over 12 times the identity. And the other block is Ricci minus scalar over 4 times the metric, which is the traceless Ricci tensor. So this vanishes. So in particular, the scalar curvature is 0, the Ricci tensor is 0, the self-dual Weyl curvature is 0. And so that implies that the full Riemannian curvature matrix of two forms anti-commutes with the Hodge-Star operator. So the gravitational terminology that arises from the analogy with general relativity. So, because Ricci is 0, so, but although we're not, general relativity is in the Lorentzian case, we're looking at the Riemannian case. And the instanton terminology arises from the analogy with anti-self-dual Yang-Mills connections. So now the curvature takes place of the connection here. Okay, so let me make a few remarks on Ricci-flatness. So we could have just required, instead of hyperkähler, just Ricci-flat Kähler. So in this case, you still have that the curvature anti-commutes with the Hodge-Star operator, but this condition is more general. So however, if you're Ricci-flat Kähler and simply connected, then that does imply hyperkähler. But notice we did not assume simply connected in the definition, so I'll give the reason for that. So, so just about Ricci-flat Kählers, there do exist isometric quotients of hyperkähler metrics, which are just only Ricci-flat Kähler. So just some example of that are finite quotients of ALE, AK type metrics, which I'll talk about in a little bit what ALE means. So there are also there are some hyperkähler examples which are not simply connected. So some examples of that. So just a trivial example is R times a 3 torus, flat 3 torus. This is just flat. There's a metric known as the Atiyah-Hitchin metric, and that lives on S4, the complement of a Veronese embedded RP2 inside of S4. So there's another class of instantons, which I'll talk about in a moment, called ALH star instantons. So one example of those live on CP2 minus an anticanonical torus, and also the complement of an anticanonical torus in S2 times S2. So those are not simply connected. So this is the reason we don't want to put simply connected in the definition. So well, we could have also just required the Ricci-flat condition and just forget the Kähler condition, but I didn't do this because there are just not many known examples which are not Kähler. So then some interesting examples of these, there's the Euclidean Schwarzschild or Euclidean Kerr metric. Those live on, the topology is R2 times S2. So, so those are, you take the general relativity Lorentzian solutions and you do what is called a Wick rotation. You replace time with an imaginary time, and then you actually get a Riemannian metric, which is Ricci-flat. There's another interesting example, but due to Page, it's called the Taub-Bolt metric, and this lives on the complement of a point in CP2, and this is the total space of O minus 1 over P1. So that is a non-Kähler metric, though. And then Picard and Minerve have an interesting construction. They can take a quotient of a hyperkähler example, which is not even Kähler. And so that gives another example. But other than these, there's really not a whole lot of examples which are not Kähler. There's really some remarkable relation between Kähler metrics and Ricci-flat metrics in this dimension. So, so now let me go on to the list of examples. So we start with ALE, gravitational instantons. This was originally an abbreviation for asymptotically locally Euclidean. So we say a metric is ALE. So this is outside of a compact set. The metric is a flat metric on R4 modulo gamma, where gamma is a finite subgroup in SO4 acting freely on the 3 sphere. And then it's plus O of R to the minus delta as R goes to infinity. So just some decay terms. So just a picture. So this is, so here's the topology, which we have no condition on the interior of the manifold, but as you go up to infinity, it has to asymptote to a Euclidean cone, 4-dimensional flat cone. So that's what they look like. So let me make some remarks on these. So there's lots of examples of these. So the most basic one is the Gucci-Hansen metric. So this has the order of the group is 2, and it's the total space of the cotangent bundle of S2. So more generally, there are examples of type AK. These are known as multi-Gucci-Hansen metrics, and they're the DK, E6, E7, and E8 spaces, which have been classified by Kronheimer. So these have the property that the volume growth is maximal. Volume growth of a ball of radius r is proportional to r to the 4th. That's as r goes to infinity. The tangent cone at infinity is just that cone, R4 mod gamma. And it turns out the curvature decays better than you'd expect. It decays O of r to the -6. And so that's because you can choose delta bigger than or equal to 4. And this is a result of Bando, Kasue, and Nakajima. Okay, so those are the asymptotic properties of these metrics. So let me move on to the next class. So now ALF gravitational instantons. So the F doesn't really stand for anything. It was just the next letter after E. So here a metric is called ALF. So if outside of a compact subset, it's asymptotic to this model metric here. So it's dr squared plus r squared times the pullback of the spherical metric on S2 plus theta squared plus some decay terms, O of r to the minus delta. And where pi from S3 to S2 is the Hopf vibration, and theta is a connection form. So what you can do, you can also take quotients by zk in the fiber direction, and you can also replace S2 here by RP2 to get other possible cases. So examples of these are the Taub-Nut metric on C2. So this was, Lebrun showed that it's, well, it was known it was diffeomorphic to R4, but it's actually biholomorphic to C2. So it has, there's no topology, it's a contractible space, yet it's a non-trivial Ricci-flat metric on it. It's not the flat metric. So more generally, so there are examples of type ALF AK. So this is when you allow that ZK quotient in the fiber. So the cross section is a lens space. So these are known as multi-Taub-Nut metrics. And there are ALF DK examples. That's when you have RP2 on the base there. And these were due to Cherkis, Hitchin, and Kapustin. So the asymptotic properties of these metrics. So the volume growth is proportional to R cubed. So it's non-maximal volume growth. And the tangent cone at infinity is R3 or R3 mod plus minus 1. So turns out the curvature decays inverse cubically. So you can choose delta is less than 1, any delta less than 1 in the definition. So this is due to Minerve and Chen. And then these types of gravitational instantons were classified by Chen. So these have strictly better than quadratic curvature decay. So these are all of the examples of these types of metrics. Okay, so let's move on to the next case, but we need to do a little bit of background so I can define the next case. So this is deals with elliptic fibrations, and we'll just look at the surface case. So these are complex surfaces which admit a projection pi to a Riemann surface C. So it's holomorphic, and the generic fiber of genus 1. So we'll let S be a finite set, P1 to PK, be the image of the singular fibers. So Kodaira defines some fundamental invariants of such a fibration. So one is the monodromy. So this is a representation of the fundamental group of the complement of that finite set of points into SL2Z. Okay, so this sort of tells you how topologically the bundle, as you go around one of the singular points, it's an S1 bundle over T2, but it's non-trivial. So this tells you how to patch, how to glue together to get the non-trivial bundles around each of the singular points. So there's also the fiber is elliptic curve. So you have the periods of an elliptic curve, and that's a multi-valued function tau from the Riemann surface minus the finite number of points into H, which is here, this is the upper half plane. So the functional invariant, you can apply the J function to tau and get a function from the complement of the singular set into P1, so it's meromorphic in general. So, and it determines that, so this determines the complex structure of the smooth fibers. So these are the two fundamental invariants. So there's a compatibility between these. So as you go around a closed arc around one of the singular points, so you can take a single valued lifting of tau, and this transforms by the corresponding monodromy matrix, thought of as a fractional linear transformation. and up to plus minus 1. So these are that's the compatibility condition. So these are the fundamental invariants. So I'll refer to these a lot in the following. So Kadir classified the possible singular fibers. So we'll consider only the cases that there are no multiple fibers and all fibers are minimal. So there's no -1 curves lying entirely in the fiber. So the list is the following. I'm not going to give you the whole list, just a few cases. So there's the type called I sub b, where b is bigger than or equal to 1. So the monodromy on gamma, where gamma is a loop going one times around counterclockwise direction. So it's always conjugate to 1b01. So, and the J function has a pole of order b at the singular point. Another type, which the monodromy looks similar, it's just minus that monodromy, but this is IB star. So b is bigger than or equal to 1. So yeah, the monodromy is minus the IB type, and J also has a pole of order b at the point. So, and Kadir also described actually the fibers consist of a configuration of rational curves, and he described the configuration, but I'm not going to go into that amount of detail in this talk. So, so those first two cases are the infinite monodromy cases. So the remaining cases are a finite monodromy. So there's I0 star, 2, 3, 4, 2 star, 3 star, and 4 star. And the J invariant of these is, so it can be any number. So J extends holomorphically over the point. And so J of 0, if the singular point is over 0, so it can be any complex number in the I0 star case. So then here in there's the 2 and 2 star case. So those have J invariant 0. So that's the 60-degree lattice torus. And then the 3 and 3 star have J invariant 1, so that's a 90-degree torus. And 4 and 4 star also have J invariant 0, which is the 60-degree torus. So that I'm not going to list. So there's each of those have a monodromy generator, which consists of just zeros and ones and -1s. But let me not list that. So that's a very quick review of Kadir's theory. So, but we need that to even define this next class of examples. So we had ALE, ALF, so the next letter is ALG. So here we'll define the model metric. So G sub beta comma tau, so it depends on 2 parameters. So it's going to be the Euclidean metric plus G sub tau. So this is a sector of angle in 2 dimensions of angle 2 pi beta. So, and it's that times a flat 2 torus. So G tau is just a flat metric on the T2 torus, and then Euclidean is just a flat metric on this sector. Okay, so and then tau lives in the upper half space. Okay, so we say a metric is ALG if on a dense subset, so away on the complement of a compact set. So G is this model metric, G sub beta tau plus O of R to the minus delta plus decay terms as R goes to infinity. So you'll see why I said on the dense subset on the next slide. So that these examples arise from any rational elliptic surface. So these are elliptic surfaces with which fiber over P1 and come from a pencil of cubics in P2. So then you blow up at the indeterminacy locus and you get you blow up at 9 points. And so this is topologically P2 connects some 9 P2 bars. So, and now the total space of the ALG metrics are the complement of one of the finite monodromy fibers in such an elliptic surface, which has a finite monodromy fiber. And so then given the type of finite monodromy fiber, the beta and tau are restricted. So basically in the I0 star, we see 1/2, 2, 3, and 4, 1, 6, 1, 4, 1/3. So these are sort of orbifold the conical direction, but then there's some just rational cone angles in the star case, 2 star, 3 star, and 4 star. And then tau is also restricted, so the same in the previous list of Kodaira. So and I listed tau here. So the 2 star, 4, and 4 star have the cube root of unity as a generator, as the lattice generator, and then 3 and 3 star have I as lattice generator, and then I0 star can be any flat torus. Okay, so the sector in the ALG definition, so that has to be closed up by the monodromy around the type of singular fiber. So that's why we said just on a dense subset. So the asymptotic properties of these metrics, so it's written here, I didn't know if I said it, this was in Hein's thesis. So he showed these have volume growth is quadratic volume growth. So, and the tangent cone of infinity is just that 2-dimensional cone of the angle 2 pi beta, where beta is in this list. And the curvature tensor decays strictly better than quadratically. So then these spaces, this falls under the classification of Chen-Chen. So these are all of the examples. Okay, so we move on to the next case. So this one is ALG star. It's a little more complicated to define. So here we let B be an even integer, which I'll write as 2 times nu. So V will be the function B over 2 pi times log of R. And so I'll define this metric G sub B is V times this metric dr squared plus r squared d theta 1 squared plus d theta 2 squared plus V inverse times d theta 3 squared. So here d theta 1, d theta 2, d theta 3 are a left invariant coframe on a Heisenberg Mill manifold, which is an S1 bundle over T2 of degree B. So it's the quotient of the Heisenberg group by an arithmetic subgroup, which is Z plus Z plus Z. And so that becomes a compact manifold, and that fibers over with base T2 and fiber S1. And we require that d theta 3 is a connection form satisfying d theta 3 is b over 2 pi d theta 1 wedge d theta 2. That's the area element on the 2 torus. Okay, so that's this metric G sub B, but we're not done with the definition yet. So now let G tilde sub nu, so denote the metric on the Z2 quotient of what I just defined by the following action. So theta 1 you translate by pi, theta 2 and theta 3 get reflected, just a reflection, they go to minus. So this turns out this gives this is a global Z2 isometry of this model metric. And so the metric descends to the quotient. And then the quotient metric, the cross section of this metric will be an infranil manifold. So it's a finite quotient of a nil manifold. Okay, so now the definition of ALG star is G is this G sub nu tilde plus O of R to the minus delta plus decay terms. Okay, so where these first were shown to exist in Hein's thesis, so they arise from a rational elliptic surface, the complement of a singular fiber of the type I nu star. Nu has to be in between 1 and 4. So that's 4 is the maximal type of I star fiber that you can have on a rational elliptic surface. So these were, so they have some interesting asymptotics. So the volume of a ball of radius R is quadratic, just like in the ALG case. The tangent cone at infinity is, remember, we took this Z2 quotient in the conical direction. So the tangent cone is R2 mod plus minus 1. And it has an interesting curvature decay property. The curvature tensor decays like inverse quadratic, but times 1 over log R. So it's not strictly better than quadratic, so it does not fall under the classification of Chen-Chen. By the way, Chen-Chen is Gao-Chen and Shushang-Chen. I forgot to say that earlier. Okay, so we've got ALE, ALF, ALG, ALG star. So there's two more. We're almost done with the examples. So this next example, ALH, is actually the easiest to define. So a metric is ALH if it is asymptotic to dr squared plus g sub t3, where that's g sub t3 is a flat metric on t3. So plus some decay terms. So notice this is just asymptotically cylindrical with the cross section is flat 3 torus. Okay, so these examples arise from the complement of a smooth fiber in a rational elliptic surface. So this was also done in Hein's thesis, building on work of Tianya. So the volume growth of metric balls is linear for these examples. The tangent cone at infinity is R plus, unless you're in the splitting case where you just R times T3, in which case the tangent cone is R. So now Chen proved that actually the curvature decay of these is exponential. So that is strictly better than quadratic. So these were classified by, these fall under the classification of Chen. So these are all of the examples. Okay, one more class of examples. So ALH star gravitational instantons. So these are kind of related to the ALG star, which we defined before. So define G sub B now. This is a different G sub B than before. So it's dr squared plus r to the 2/3 times pi star of a flat metric on a 2 torus plus r to the minus 2/3 times theta b. And this is similar to before. Theta b is a connection form on a Heisenberg-Nil manifold, which is an S1 bundle over T2 of degree b. And d of the connection form is 2 pi b times the area inverse times the volume element on T2. So then we say a metric is ALH star if it is this model metric plus, so this turns out to be the correct decay rate. It's exponential e to the minus delta times metric distance to the 2/3 power. Okay, so this one I can draw you a little picture of here. So this is there's no condition on the compact piece, but as you go off to infinity, you have these Heisenberg-Nil manifolds, and the S1s shrink the further you go out, but the Nil manifolds get larger. So in terms of the distance to a base point, the diameter of the Nil manifolds is like r to the 1/3 power, and the diameter of the circles is r to the minus 1/3 power. So it has this strange doubly warped asymptotic geometry. So, so examples of these arise from, again, from the complement of some singular fiber in a rational elliptic surface. And this is when the fiber is type IB, and B is between 1 and 9. So 9 is the maximal type of IB fiber you can have on a rational elliptic surface. The volume growth, so it's interesting, it's non-integral. So it's O of R to the 4/3. The tangent cone at infinity is R plus. It's interesting, the curvature decays inverse quadratically, but it's not any better. So these also do not fall under Chen-Chen's classification. Okay, so that finishes the examples. Okay, so now I'm going to talk about some relation of these examples with K3 surfaces. So let me give you a quick review of K3 surfaces. So, if X is a compact complex surface, which is simply connected and has a vanishing first Chern class, then it turns out X is diffeomorphic to a quartic hypersurface in P3. So there's only one diffeomorphism type. So by Yau's theorem, every Kähler class for every complex structure admits hyperkähler metrics. So, well, they admit Ricci-flat metrics, but now this will be a Ricci-flat Kähler metric. It's simply connected, so it has to be hyperkähler. So the dimension of the moduli space of the Ricci-flat metrics on K3 is 58. So just heuristically, so K3 has a 40 real dimensional space of complex structures on it. And for each complex structure, you have a 20-dimensional Kähler cone. But now we subtract 2 because the metric is hyperkähler. Okay. And so note this 58 includes scaling. If we modulus scaling, it would be 57-dimensional. So it's known that, so this was in Oshima's talk yesterday, so the moduli space is isomorphic to a homogeneous space modulo and discrete arithmetic subgroup. So, and this is in Grassmannian. So you take the identity component of SO319 mod SO3 times SO19, and then you have to mod out by this subgroup. I'm not going to get into details of this, but roughly the second cohomology is 22-dimensional, and then it's hyperkähler, so the 3 Kähler forms span a positive definite subspace. So then that subspace is so you get this Grassmannian of positive definite 3 planes in this indefinite 22-dimensional space. So, and note that this description includes orbifold K3 Einstein metrics. Okay, so we're interested in what happens near the boundary. So Yau's existence theorem is an abstract existence theorem. It doesn't tell you what the metrics look like in the interior, but we have some hope of describing all the degenerations near the boundary. So take a sequence of Ricci-flat metrics. It's known. You can get a Gromov-Hausdorff limit. So singularities have to form, so that means the curvature blows up. So then when the curvature blows up, you can rescale to get bounded curvature, and you get what is called bubbling phenomenon. So these are, and the non-collapsed rescaled limits that you get are going to be gravitational instantons. So they'll be complete hyperkähler spaces with finite L2 curvature. So the theory divides into 2 cases. So there's the volume non-collapsing case. So when volume of balls is bounded below by a positive constant, it's known you always get an orbifold limit. So this was done by Anderson, Tianya, and Bando, Kasue, and Nakajima. So we're going to be interested in the volume collapsing case. So when the volume of unit ball goes to 0, and then in that case you have to get a lower dimensional limit. So a very important theorem is that of Krieger-Tianya, which says that, so in this setting, any such sequence collapses with uniform bounded curvature away from finitely many points. So they proved an epsilon regularity theorem without requiring a Sobolev constant now. So we'll just see that. So their theorem tells you what happens away from the singular points, but it doesn't give you any information about what happens near the singular points. So I'm going to give lots of examples now, which can tell you what are the possible types of degenerations which can happen near those singular points. That's what we're interested in. Okay, so now let's go back to the examples, and I'll show you how each case can arise from a K3 surface. So first case was ALE. So this is the case where you're asymptotically conical. So the well-known example of this is the Kummer surface. So there are sequences of Ricci-flat metrics on K3 which have a 4-dimensional limit. So these are volume non-collapsed. So and the limit is just the flat T4 modulo and involution. This has 16 singular points, and when you rescale the sequence near those singular points to have bounded curvatures, you see Iguchi-Hansen metrics bubbling off. So this picture tries to indicate what happens. So this is the orbifold limit, and this is an Iguchi-Hansen metric. So you scale down the Iguchi-Hansen metric and glue it on here to resolve the singularity, and then it looks like this near each singular point. Okay, so sorry, I don't have lists, there's probably lots of people I should reference here, but sorry if I did not reference you. So in the next case, ALF bubbles. So recall that the ALF case is where it was asymptotic, so in the Hopf vibration, so the base directions grow like in Euclidean space, but the circle fiber goes to constant length at infinity. So these were shown to bubble off of K3 by Foscolo. So he did a modified Kummer construction where you can obtain a three-dimensional limit. So basically let one of the S1s and the 4 torus collapse, and the three-dimensional limit is T3 mod Z2 with the flat metric. And in the simplest case, there are 8 singular points, and you get ALF D2 metrics bubbling off. So you can, he can modify this construction to get more complicated ALF bubbles and also ALE bubbles, but I'm not going to go into all the possible cases here. So in the next case, so I'm going to skip ALG, we'll come back to that. I'm going to go to ALH. So this was the case which was asymptotically cylindrical on a flat 3 torus cross section. So Chen showed that there are sequences of Ricci-flat metrics on K3 which have a one-dimensional limit, which is just a one-dimensional closed interval. So their singular points only are at the endpoints. So this is like in Cheeger-Tian's theorem. So away from the singular points, you get collapse with bounded curvature. And in this case, it's just uniform shrinking of flat T3s. But then at the endpoints, these ALH metrics bubble off. So, so these were produced by gluing together 2 asymptotically cylindrical metrics with a long cylindrical region in between. And this was using earlier ideas of Kovalev, Singer, and Flohr. Okay, so that's ALH case. Those are known to arise from K3. So next, I'm going to take a little detour here and talk about the Tianya metrics on del Pezzo surfaces. So on the complement of an anti-canonical divisor. So dp sub b will be a degree between 1 and 9 del Pezzo surface, and T2 will be a smooth anti-canonical divisor. So Tianya showed that the complement admits a complete Ricci-flat Kähler metric, which is asymptotic to a Calabi-Yau metric on a punctured disk bundle and the normal bundle around the divisor. So just roughly, they constructed a solution. So solving Monge-Ampere equation. So they took log of norm squared of a defining section of the divisor to the 3/2 power dd bar. So that was the base approximately Ricci-flat metric, and they were able to add dd bar of a function to find an exactly Ricci-flat metric. So what we would like to do is glue 2 of these together, but the asymptotic geometry of these is not cylindrical. So you need to find an appropriate neck region. Okay, so it turns out that these Tianya metrics are ALH star type, which I defined earlier. So this is joint work with Hans-Joachim Hein, Song Sun, and Robing Zhang. So Tianya metric on the del Pezzo minus T2 is ALH star. So this is just the definition of ALH star. So for some delta bigger than or equal to 0. So these give examples of ALH star metrics. So now our main, so the proof of this is a bit technical. We need to find improved asymptotics for the complex structure, and then we use the techniques in Hein's thesis and Tianya. But let me not go into details of that. I want to state our main theorem here. So this was HsvZ. So given 2 integers, b plus and b minus, in between 1 and 9, there is a family of hyperkähler metrics, G beta on K3 surface, which collapse to an interval. So this is just like in the Chen ALH case. So in that the Gromov-Hausdorff limit is an interval. So but has the following properties. So now the bubbles at the endpoints of the interval are now the Tianya metrics on del Pezzo surfaces of degree b plus minus an anti-canonical elliptic curve. So b plus on one end and b minus on the other end. So, and now in the interior region, now in contrast to the Chen-Chen ALH case, there are singular points in the interior of the interval. And so there are B plus plus B minus Taub net bubbles. Okay, so let me not say too much about the proof. I'll just give you a picture of K3. So this, if you just look at here, this was the picture of the ALH star metric, which I gave you before. So you take two of these and put them together, but the asymptotic geometries don't fit. But we found this neck region, which can be used to is a approximate Ricci-flat metric, which we can glue in and merge these together and get a K3 surface. Okay, so let me just make a few remarks, running low on time here. So this neck region we produced by the Gibbons-Hawking ansatz over T2 times R. So that's Gibbons-Hawking ansatz uses a flat base. And we found a harmonic function which is asymptotically linear in Z on each end, and with B plus plus B minus monopole points in the interior. And so that's where the Taub net metrics come from. And so this harmonic function then interpolates between the asymptotic geometries of each end. So an important point is we use the technique of gluing hyperkähler triples, not Monge-Ampere techniques. So this was a technique introduced by Donaldson and also used in Foscolow's work. So now in the regular collapsing region, so away from the singular points in the interval, so nil manifold collapse occurs. So the T2 directions and the S1 directions shrink at different rates as you go to the limit. So the diameter of the nil manifold is like beta inverse, and the diameter of the S1s is like beta to the -2. Okay, so that is ALH star case. So now let me, in the remaining couple of minutes, talk about the elliptic case. Gross-Wilson considered the case of elliptic K3s with 24 fibers of type I1. So I1 is the nodal cubic. They show you get a two-dimensional Gromov-Hausdorff limit, which is S2. So away from 24 singular points, the sequence collapses with uniformly bounded curvature. It's just the T2 fibers being uniformly scaled down. And so Gross, Tosati, and Zhang generalize this to any elliptic K3. The Gromov-Hausdorff limit is S2. Then Odaka and Oshima made further progress. But so we're interested in the case, what happens near the singular fibers? What are the bubbles? So in joint work with Gao Chen and Robing Zhang, we showed it's possible to generalize the Gross-Wilson construction to any elliptically fibered K3 surface. So, and we can understand the behavior near the singular fibers. So in particular, in the Gross-Wilson case, we can show that at the 24 singular points, Taub nut ALF metrics bubble off. Okay, so let me state the theorem. So joint work with Gao Chen and Robing Zhang. So for any elliptic K3 surface, there exists a family of Ricci-flat Kähler metrics with the following properties. So that just like in Gross-Wilson, the area of a regular fiber is fixed and it just collapses down to S2 with the MacLean metric, so away from the singular fibers. But so near the singular fibers with finite monodromy, so that was the I0 star, the 2, 3, 4, 2 star, 3 star, and 4 star. So the bubbles are the ALG gravitational instantons. So recall those were on rational elliptic surfaces minus certain singular fibers and finite monodromy. So near the singular fibers with infinite monodromy, so there's the IB case, in which case you get B Taub nut bubbles. And in the IB star case, you get B Taub nut bubbles plus 4 Iguchi-Hansen bubbles. So we can understand the bubbling near any type of singular fiber. Okay, so let me I'm almost out of time, so let me kind of skip over this. So away from the singular fibers, there's an ansatz to write a hyperkähler metric, which is called the semiflat metric. It was due to Green, Shapiro, Baffa, and Yau. And so if the fibers are smooth, you can write down an ansatz here, which is hyperkähler metric, which is exactly a flat metric on the fibers. Okay, and then the base metric is some metric involving the periods, but let me due to time, I'm going to skip over this slide. My apologies. So this semi-flat metric is singular near the singular fibers. So to resolve, so near the finite monodromies, we glued in the asymptotics of the dual isotrivial ALG metrics agree with the asymptotics of the semi-flat metrics. So that's why the ALG metrics are the right thing to resolve the singularities. So then, near the infinite monodromy, we sort of just extending what Gross and Wilson did. Instead of Oguri-Vafa metric, you glue a multi-Oguri-Vafa metric, where you have more monopole points. So then in the IB star case, it's a little bit complicated. You have to take the quotient of a multi-Oguri-Vafa metric modulo a Z2 action, kind of like I defined exactly like I defined in the ALG star case. Okay, and then you get 4 ordinary double points, and you need Iguchi-Hansen metrics to resolve those. Okay, let me do this really quick. So for any elliptic K3 surface, this is some recent work in progress. So we have a different construction near the singular fibers of type I nu star, of IB star. So near a singular fiber of type IB star, so for an elliptic K3, you can have at most an I14 star fiber. So then given any integer between 0 and 4, we can construct a sequence which has ALG star gravitational instanton bubbles plus B plus nu Taub nut bubbles. So the idea of this, so we can't do this with a fixed complex structure. The previous theorem we could. But the idea is similar to the HsvZ construction, but it's a Gibbons-Hawking over a different base. So the base is R2 times S1 with the suitable harmonic function, and we construct a neck region which interpolates between the semi-flat metric near the IB star fiber and the ALG star bubble. So that, unfortunately, I'm almost out of time. Let me just do the last slide here. So let me summarize everything, the known limits. So ALE bubbles are known to happen. So the example is the Kummer case, but there are more general bubbles that can appear. That the Gromov-Hausdorff limit in the Kummer case was T4 mod Z2. ALF case, so this was Foscolo's construction. The Gromov-Hausdorff limit was T3 mod Z2. So ALG bubbles came in just the theorem of that I mentioned earlier. So the Gromov-Hausdorff limit is S2. So ALG star bubbles, so this is that work in progress, which I just described. So for nu in between 1 and 4 can also occur. So ALH bubbles arose in Chen-Chen's. ALH B star arose in HsvZ. So basically these are all of the examples constructed in Heim's thesis. So we now know that they can arise as bubbles from K3 surface. So let me end here with the following couple of questions. So are there any other possible collapsed Gromov-Hausdorff limits? So T3 mod Z2, S2, or the interval. So this is related to Odaka and Oshima's conjecture from the talk yesterday. So they conjecture that these are all the possible limits. So, but they've proved some cases, but it is as yet unknown in generality, in full generality. So, and another question, are there any other possible gravitational instanton bubbles which can arise from K3? So all of sort of the known ones now are known to arise, but there are maybe some unknown, as of yet unknown bubbles that could arise. So, so I am a bit over time, so I would like to end there, and thank you very much for your attention.